If you recall, yesterday we had 3 fourth-degree polynomials, all with positive leading coefficients. I didn't want that to be the difference. And we had some questions about critical points. Some of the things that we may or may not remember about polynomials and their graphs is that the graph of an nth degree polynomial makes at most n minus 1 terms, or is fewer than that by an even number. So the number of turns in the graph of an nth degree polynomial is equal to 1 less than the degree, or is less than that by an even number. So for a fourth degree polynomial, maximum 3 turns, and it could be less than that by an even number. So 3 turns or 1 turn. This makes sense if we think about the graph of an even degree polynomial. I'm going to use fourth degree because there's some space to work with. It makes sense because the graph of a fourth degree polynomial, as x goes to negative infinity or as x goes to positive infinity, those two ends are going to go in the same direction. So the ends, I'm going to put that in quotes. Outside of any turns that the graph might be making, the ends have to go in the same direction. As x goes to infinity, the graph goes to infinity. As x goes to negative infinity, the graph goes to infinity. Or if we multiply by -1, just negative infinities. So the ends have to go in the same direction. We want to think about this in terms of critical points, because we're in calculus now, so we know more stuff. We know that the terms are going to show up as critical points. A turn is going to be a local max or a local min, a place where the graph is changing direction. When that's happening, we're going to see critical points. We should note that not all critical points are going to represent turns, but all turns will be represented by critical points. Not all critical points are turns. But all turns are critical points. So we do want to make a note that not all critical points represent terms, but all turns will be critical points. So right now we know that this fourth degree polynomial has to make 3 or 1 turns. It has to be an odd number because the ends have to go in the same direction. The only way for the ends to go in the same direction is for the graph to make at least 1 turn at some point. If it makes 2 turns, then the ends are going in the opposite direction. That's not okay. So we have to make a 3rd turn. That's why an even degree polynomial will definitely have an odd number of turns. Turns. Stupid n and I blame English. So now that we've got these turns are going to be based on critical points, since we're dealing with a 4th degree polynomial, the derivative of a 4th degree polynomial will be a 3rd degree polynomial. The derivative of a fourth degree polynomial will be a third degree polynomial. So that x to the fourth will drop down to a 4x to the third. The reason that we care about this is that the first derivative of our polynomial, the first derivative, is going to tell us where the critical points are. The zeros of the derivative tell us about the critical points of the function. So what we care about the derivative is not so much the terms that the derivative is making, but the zeros of the derivative. So the zeros of derivative third degree derivative, a third degree polynomial is the derivative, and we care about the zeros of this derivative because that's where we're going to find the critical values. So now we have traded our problem in for terms in the graph of a fourth degree polynomial for the zeros in a third degree polynomial. Here's what we know. We know that a third degree polynomial has 3 complex zeros counting multiplicities. A third degree polynomial will have 3 complex zeros counting multiplicities. So this gives us a short list of what could possibly happen with the zeros of our polynomial. This in turn will tell us about the critical points of our original function, our fourth degree polynomial function. Counting multiplicities, so repeated zeros. So let's list off everything that could happen. There's only 3 additional piece of information. We should remember that complex zeros come in conjugate pairs. So if you have one complex zero to a polynomial with real coefficients, then you have 2. And they come from the same quadratic. They'll always be conjugate pairs, A plus or minus B times I. So the complex zeros come in conjugate pairs from the same irreducible quadratic factor. Now we're just going to list what could possibly happen. Question? That's the fundamental theorem of algebra. An nth degree polynomial has n complex zeros counting multiplicities. Each zero will be a factor in the polynomial. If we have a third degree polynomial, it can have 3 factors with complex coefficients, but no more. The multiplicity part means that one of those factors could be squared. So it could be that we have It could be that we have 3 distinct real zeros. It could be that we have 3 distinct real zeros, which means that for example, I'm just going to use an example. X minus 3 times x minus 1 times x plus 1. Each real zero will correspond to a factor. It could be that we have 2 distinct real zeros, one of them with multiplicity 2. It could be that we have 2 distinct real zeros, one of which has multiplicity of 2. That means it would come from a squared factor. So I might have x minus 3 times x plus 1 squared. There's a repeated 0 with multiplicity 2. If a 0 has multiplicity 2, then the factor from which we find it will be squared. It could be that we just have 1 real 0 with multiplicity 3. So our zeros would be -1, -1, and -1. In this case, it's repeated with multiplicity 3. A 0 with multiplicity 3, the factor where we get the 0 with multiplicity 3 will be cubed. These are all the possibilities where we just have real zeros. Everything, all the zeros are real zeros. If I want to introduce a complex 0, then I have to introduce 2 complex zeros. Because complex zeros come in conjugate pairs, unless my polynomial has complex coefficients, at which point, that's an entirely different calculus class if we're dealing with functions with complex coefficients. So the other thing that could happen is that we have 1 real 0 and a complex conjugate pair of zeros. The other thing that could happen is that we get one real zero and two complex zeros. For example, x plus 1 and let's say x squared plus 1. Our zeros would be -1 plus and minus I. They're the complex zeros showing up in conjugate pairs, 0 plus or minus 1. The complex conjugate zeros come from the same irreducible quadratic factor. Plus and minus I. The complex conjugate zeros will come from the same irreducible quadratic factor. Is everybody okay? Everybody remember polynomials? I don't know if you did polynomials in this much detail. This might get into Descartes' rule of signs. Everybody remembers Descartes' rule of signs, right? I'm just kidding. No one ever knows. Does anybody actually know Descartes' rule of signs? No one does. It's weird that I know. I did not learn it in algebra, by the way. So if you think, oh, I've been through all my algebra classes, elementary algebra, calculus. Why did this never show up? Because graphing calculators happened. And someone didn't think it was important. I was tutoring a student once, and they had a very old calculator book, pre-calculus book actually. And it's like, oh, Descartes' rule of signs. I'm like, oh, what? So. I'm totally not surprised. Did everybody know who knew the rational zero theorem before I mentioned it yesterday, or whenever I mentioned it last week? Anybody know the rational zero theorem? You might have heard of it. I'm just talking about have heard of it before. When I'm like, oh, here are the possible zeros. And then you probably did like synthetic division. Does everybody remember synthetic division? If you know what synthetic division looks like, if you can kind of just picture it, don't have to do it. I'm not going to give you a quiz about it. You don't have to do synthetic division, but if you can imagine what synthetic division looks like, you probably did learn about the rational zeros theorem. You just don't remember. Does that make sense? It's just something that you forgot. It's like when parents on Facebook be complaining about their kids and not knowing how to do their kids' math homework. It's like, well, someone tried to teach you, you just don't remember because it hasn't been important enough to you to actually remember. So don't get mad. Just like, it's not a big deal that you forgot something that you don't do all the time. It'd be kind of weird if you did, or you'd be a math teacher if you did, you know what I mean? But a math teacher wouldn't be up on Facebook complaining about it because a math teacher would be like, oh, I don't know how to do that, kid. You're on your own. And then you go back to playing video games or whatever it is people with math teachers with kids do. I don't know. I have a dog. They're much easier. They don't have to go to like math school, which is excellent. Here's one of the things that we want to notice about everything that can happen. Now, notice that we can't have 3 complex zeros because the complex zeros have to come in conjugate pairs. It's got to be an A plus or minus BI. I can't have a third one be like, oh, just A plus BI, because A minus BI has to go with it. If I'm going to have three complex zeros, I have to have 4 complex zeros, but I've only got a third degree polynomial. There's not enough space. My factors can be linear, 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 or linear and quadratic. That's it. That's the end of it. So here's what they all have in common. All of these possibilities have at least one real zero. All 4 of these cases have at least one real zero. Let's combine that with what else we know about a third degree polynomial function. With a third degree polynomial function, the ends have to go in opposite directions. With an odd degree polynomial, like a third, the ends have to go in opposite directions. Because if I take negative infinity to the third power, I get negative infinity. If I take positive infinity to the third power, I get positive infinity. If I multiply by -1, they're still going in the opposite directions. So the ends of a third degree polynomial must go in opposite directions. Therefore, that one real zero, at least one real zero, represents the graph crossing the x-axis, changing sign from negative to positive or positive to negative. Let's use a math word, thus. No one says thus except mathematicians. Thus. The derivative must change sign. There is one real zero, and it's not one of those vertexes on the x-axis things. The third degree polynomial has ends going in the opposite direction. That means at some point it has to come crashing through the x-axis, changing sign from negative to positive or positive to negative. Thus, our fourth degree polynomial must have at least one term. So we see that all the stuff that we know about polynomials supports the stuff that we've just added to it. Today, we didn't learn anything new about polynomials. We've made sure that the new stuff that we learned about polynomials recently, this derivative business, matches with what's going on with what we already know about polynomials. Questions? Is everybody okay? All right. We got these 4 cases of real zeros. let's draw pictures of the derivative and then use the derivative to draw possible fourth degree polynomials. I want to cut my drawing in half. And I'm just going to look at a positive leading coefficient. Let's just worry about a positive leading coefficient. One of the things that could happen is that we get 3 distinct real zeros. So it could be that our derivative, a third degree polynomial, has 3 distinct real zeros. Oops. Now, at each of those 3 real zeros, we can see that the function is going to be changing direction. That first one, it goes from negative, the derivative goes from negative to positive. So the function changes from decreasing to increasing. The second one, the derivative goes from positive to negative. So the function changes from increasing to decreasing. And the third one is the reverse. I don't think I'd be able to correctly say it a third time. So our function goes from decreasing to increasing to decreasing to increasing. There are 3 terms, each corresponding to the zeros of the derivative. Notice on this one, I did not write an x-axis because we don't know that constant. We don't know where the constant is going to put this function. The other thing that could happen in the derivative is two distinct real zeros, one of which gets repeated. So here's one. And then the other one, if it's going to be repeated, I'm going to have to do this. I have to go back down, touch the x-axis once, and then bounce. Let's go 2 real, 1 with multiplicity 1, 1 with multiplicity 2. Notice that in this case, our graph of the function is going to go from decreasing to increasing, go flat, and then continue increasing. So we're going to go from decreasing to increasing. This other 0 in the derivative means the graph's going to go flat, but then continue to increase. third option with the real zeros. Third option for our derivative. We could have one real zero with multiplicity 3. This is your traditional x cubed graph. So our graph is going from decreasing to increasing. Here we'll just have the one term. It will be extra flat though. Notice that our derivative is increasing except at the point where it turns. So we got increasing, then the derivative goes flat and then continues to increase. So our function is going to be concave up and then concave up again. There'll be that one point where there isn't any concavity, but everywhere else is concave up. That's what making that turn really flat. Or one turn that's really flat. Any questions? These are the three cases that you found on the three functions yesterday. That first one is the f of x type. The second one is the g of x type. And the third one is the h of x type from yesterday. Oops. That leaves the fourth one. So we got to think about what that would look like. What if we had x minus 1 times x squared plus 1 for a derivative? That's the one that we didn't do. I didn't actually say what I wanted correctly because I wasn't reading things properly. The product of the sum of x and 1 and the sum of the square of x and 1. I think I said that. This is, by the way, why we came up with all this notation. We invented algebra so we wouldn't have to describe things in words. You know what I mean? Like if I ask you what the Pythagorean theorem is, it's really convenient for us to be able to just go a squared plus b squared equals c squared. Rather than the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. We would all just rather say a squared plus b squared equals c squared. Also, it's super more convenient to be able to convert that into the law of cosine. C squared is a squared plus b squared minus 2ab cosine of gamma. Because the law of cosines is just the generalized form of the Pythagorean theorem, or better, the Pythagorean theorem is just a right triangle version of the law of cosines. So if you're like if I'm like do you know the law of cosines? And you're like, no, I'll be like, incorrect. Because you know the Pythagorean theorem. So you know it for at least one case, that of a right triangle. So give yourself a break. You know all kinds of shit. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.